What's up? Today we're going to talk about singular points and series solutions of differential equations, and we're going to talk about finding the radius of convergence for those solutions around ordinary points. So first of all, we got to talk about what is a singular point. A singular point is an x value that makes this leading coefficient 0 for our differential equation. So if our differential equation is a2 of x y double prime plus a1 of x y prime plus a0 of x y equals 0, a singular point is just any x value that makes this leading coefficient a2 0. If we look at an example here, we have maybe something like x squared minus x y double prime plus y equals 0. Then our a2 of x is just x squared minus x. Well, I go ahead and factor that as x times x minus 1. Then the two singular points for this a2 of x are 0 and 1. So we got two singular points for this differential equation. Now, whenever we're solving differential equations, we have singular points and we have ordinary points. Anything that's not singular is called an ordinary point. So let's just mention that right here. So any point that is not singular is called an ordinary point. So any point that is not singular is called ordinary. So we'll find solutions about singular points, we'll find solutions about ordinary points. Mostly what we're going to talk about right now is finding, or at least the radius of convergence for a series that is expanded around an ordinary point. So it's really good to be familiar with power series, and here's the general form of a power series, and this is what we're going to assume our solutions have the form of, as far as ordinary points go at least. When finding a power series solution around an ordinary point x0, we assume the form of the solution to the differential equation is just a normal power series, Cn x minus x0 raised to the nth power. So that's going to be the form we assume. And then we might say, what's the radius of convergence of that power series? So the radius of convergence is the distance from the ordinary point x0 to the nearest singular point. So we need to know the singular points of the differential equation to know what the radius of convergence is for the power series. So once we find the nearest singular point, we just take the distance to that, whatever that means. We'll look at an example, a couple examples to figure out how to do that. So let's look at some examples. All right, to find the radius of convergence for a differential equation solution, we need to look at the ordinary point about which we're expanding and the singular points of the differential equation. So find the radius of convergence for a solution y equals the sum, n equals 0 to infinity, Cn x minus 1 to the nth power. So the solution is going to be for the differential equation x squared y double prime plus y prime plus xy equals 0. So we want to say, okay, this point x0 equals 1, is that singular or is it ordinary? Well, that's an ordinary point. So this is not making the coefficient of y double prime 0. So x0 equals 1 is an ordinary point. The singular point, actually there's only one. The singular point is x equals 0 is a singular point. That's actually the only singular point of this differential equation. So the only singular point of this differential equation. Now, what's the distance between these two? Well, we would just take the absolute value of, we'll just say 1 minus 0. So then that's just 1. So the radius of convergence here would just be 1. So that's the distance from this ordinary point x0 equals 1 to the nearest singular point x equals 0. It's not always that easy, so look at a little bit tougher example next. All right, so here we've got another example. It says find the radius of convergence of the solution. The sum, n goes from 0 to infinity, Cn x minus 1 to the n for the differential equation. Here we've got the leading coefficient x squared plus 2x plus 5, y double prime plus xy prime plus y equals 0. Now we need to find the singular points again. Is x0 equal 1 a singular point? I don't think so. If I plug that in, I get 1 plus 2 plus 5, that's 8. That's definitely not 0. So what are the singular points? Well, singular points are when this thing equals 0. So I set x squared plus 2x plus 5 equal to 0. See if we can find what the singular points are. I don't think this is going to factor. 5 is prime, so we're going to have to use the quadratic formula. So x1 and 2 are going to be negative 2 plus or minus the square root of 4 minus 4 times 5 is 20 all over 2. So that's going to be negative 2 plus or minus square root of negative 16 all over 2. This is equal to negative 1 plus or minus 2i. All right, so we got complex singular points. What do those look like? Well, those are going to be in the complex plane, so let's draw those in the complex plane. All right, so we got our singular points. We got x equals negative 1 plus or minus 2i. If we draw those in the complex plane, let's say this is the real axis, here's the imaginary axis. Let's say this is 2i, this is negative 2i, and this is negative 1. Then our singular points are right here and right here. And our ordinary point is over here on the x-axis, or on the real axis at x equals 1. So we want to find the distance from 1 to the singular point. And actually these two are the only singular points, so the distance here is actually the same as the distance down here because those complex numbers are conjugates of each other, and this point 1 is on the real axis. So that distance is going to be the same regardless of which one we use. Now how do we find the distance between a number on the real axis and a number in the complex plane? Well, it's actually very similar to finding the magnitude of a vector. So actually I can take the modulus of the complex number 1 minus negative 1 plus 2i. And when I add complex numbers or subtract complex numbers, it's basically like doing vector addition or subtraction. So when I take the modulus of this complex number, that's actually just going to be just like taking the length of a vector. So when I do this vector addition, if you want to think of it like that, I'm going to get the number 2 minus 2i. So when I do 2 minus 2i, I take the modulus of that. That gives me 2 squared plus negative 2 squared, which is equal to the square root of 4 plus 4, which is the square root of 8. And we can say that that's 2 square roots of 2. So our radius of convergence would be 2 square roots of 2 for this solution to our differential equation. And that's it. That's how we do it.